My name is Nathan Sturdivant, and this is a talk that is based on the master's research that my student Junwen Shen did at the University of Alberta. And Junwen is now continuing on to the PhD program here with me. And this is a paper that he submitted, or that we submitted to AIIDE 2024. However, he was unable to get a visa to go there, and so I presented his work for him. And since I gave the talk there, I decided I'd make a recording and add it to my YouTube channel as well. And I'm very happy to announce that his work was awarded the Best Paper Award at AIIDE. And so we're really happy to see that he got that recognition for this work. The Best Paper Awards this year were done by a vote from the audience. And yeah, so you get to see some of the work that he did here. And let's go ahead and get started. I will say this is about a week after the conference, and I will go through this probably a little bit slower, but it was a 15-minute talk for the actual conference, and so it was designed in terms of some of the details that were presented and things like that, to not go over all the full details, but the paper is available on our webpage, on my webpage, so you can go look at the full details there if you're interested in it. Okay, so what are we looking at here? In particular, what we're looking at, and the reason why we targeted the AIIDE conference, is we're looking at solving puzzles and trying to determine how hard is a puzzle going to be for a human player. So this is a question that has really broad implications, and there's a number of approaches that have been developed to do this in the past. They've used problem-specific methods, things like what is the size of the tree, or the solution length, or things like this. And if you have a measure like this, there's dozens of algorithms that you could use, genetic algorithms or other algorithms, that this can be used as a measure for finding puzzles that would be interesting for humans to play. And in this talk, we're building on some work by another master's student of mine, Eugene Chen, who presented last year. And he looked at a measure of entropy to say how much entropy is there in a puzzle. And we're going to extend that in this talk to talk a little about a little more broadly than that, and we'll use a notion of information instead of entropy, because it will give us a slightly more broader ability to talk about things like policies. Okay, so the other thing is that as a result of this, we're going to have some theoretically grounded algorithms, and it ends up that the results that we come up with are very simple, and so that's really nice. It means that I'm not going to go through the full derivations, but he did some optimizations, Junwen did, and in the end, the math is very easy to try to measure the information that it takes to solve a puzzle. So we're going to build the first thing we need to do is define the problem. We're going to build a model of a puzzle, which helps us to define that problem. So we're going to say that a puzzle is defined by a start state. Now here in most of this talk, we're going to use examples from the game The Witness, although you don't really need to understand the technical details. Here, though, we're drawing paths, and in the start state, the path is starting in this area down here. And when we get to the goal, then in the goal state, the path is reached. In this case, we put this little notch here is the goal. The notch can be at other locations. It's usually in the upper right-hand corner, but for the fun of it, we put it here today. So puzzles defined by a start state, by a goal state, a successor function. A successor function basically tells you what actions you can take. So in this puzzle, you can move the path to the right, or you could move the path up, and then continue throughout the tree. If you notice here, this does exactly make a tree, right? We have a start state, the actions you can take from there. The next state, you're going to be able to move up and right from each of those states, and this will continue throughout the puzzle. So puzzle's modeled then by a tree, and the goal is to find a path that gets you between the start and the goal. Now, since we know this is a tree, we're going to move a little bit more abstractly, and we're just going to think about a tree here. We're not going to think about exactly the states that each of these nodes represents in the tree. And I want to talk about what is the work that we published last year, and what is the model that it uses for thinking about the difficulty of a problem. And the model it uses is, you can imagine that we have an oracle, and an oracle is communicating with the player who's playing this puzzle. And the idea is the oracle is telling the player the actions that they need to take. So at each point in the tree, the player is going to ask the oracle. So we have a start here and a goal here. And at the top, the player is going to come and say, I need to either go left or right on this tree or take one of these actions. And the oracle is going to say, hey, in this case, you should go to the right. So, and then now, once we go to the right, we have two decisions again to go to the left or the right. The oracle will say, in this case, go to the left. In this case, then we could just keep going straight. There's no choices there. We go to the right. We continue down the tree. And the oracle eventually will take us all the way to the goal. So what we're asking is, how much does an oracle need to tell us to solve this problem? And so we can think about, along the way, how many decisions did an oracle tell us about? So was it the root, and then here's a second node, a third, a fourth, a fifth node. At the other nodes, there were no decisions that were being made, so there were only 5 decisions that we needed to make with the help of the oracle. And so Muse and Remuse were these older versions of these algorithms. Said, look, there's 5 decisions we're making. On each of these particular decisions, there's 2 choices. So we can measure the entropy here. And when we add it up, we get a total entropy of 5. And that's the number of, basically the number of bits or Shannons that are communicated to the player to help them solve that problem. So along with that, in previous work, we introduced the notion of having entropy rules. And so I'm going to introduce one entropy rule, or one inference rule that came from previous work and one that came from our current work. But the idea here is that a player may not be totally oblivious between decisions. And so in the previous work, we added the ability to have basically a binary inference rule that tells us either that there's some actions that we have to take. So in this case, we have our path coming up. In the solution, the squares, which are rounded squares, which are blue and black, are required to be separated by a path. And so in this case, if I don't separate them now, I'll never be able to separate them. So I must take this action. And so although nominally there's 2 actions that we can take in the puzzle, in practice, we can only take one because we know we have to take this action. So we can represent player knowledge by having this inference rule. There's another type of inference rule we can have. In this case, we know actually that the 2 black pieces here, this one and this one, need to be in the same region at the end of the solution. And so if we move to the left right here, then they won't be in the same region, and so that's an action we can't take. So we consider this, we say, here's an action you should never take. But there still are 2 actions to choose between. So sometimes we eliminate actions, sometimes we require you to take actions. And, so these are some of the ideas in the previous work. And if we look at this tree, we could see these locations here where there were these branches that are cut off. And these are essentially equivalent to places where an inference rule has told us, yeah, you don't need to try that action, even though it'll take you to some state, it's some state that you would never consider. Okay, so in this paper, we're going to ask a theoretical question about, how do we need to modify some of this previous work to be able to handle policies? We're going to ask a practical question that says, there's previous work that's learned some policies for machine learning, and we want to understand what they're learning. And we also built a tool that uses something called exhaustive procedural content generation, and we'll see that tool near the end of the talk. And we were actually building this tool to be guided by this total solution information, which is this concept we're going to develop in this talk. And I'm going to only cover this at a relatively high level here, but if we look at the previous work, it could only handle uniform policies. And so with a uniform policy, we could look at this choice that we have, and we'd say, yeah, there's a 50% chance of the player, for instance, taking each of these actions. So we assign a 50% probability there. When we measure the entropy is 1. But suppose that we now have a policy. We want to use a policy to evaluate. A player may say, this is the action I think you should take, or we have a model of a player doing that. And so we say, well, one action has a probability of 1/5, and the other one has a probability of 4/5. If you measure the entropy, it says, well, there's entropy of 0.72 here. But this actually sort of doesn't quite tell us what we're interested here. So I'm pointing this out to show us, what did we have to fix about this? Why can't we just use exactly the same model? And the issue is if the goal is on the left side, then the problem's going to be harder for the player to solve because their policy doesn't want them to go that direction. Whereas if the goal is on the right-hand side, it's going to be relatively easy to solve. And so between the left and the right side of this particular tree here, we need to distinguish between whether we're taking, the harder thing relative to our policy or the easier thing relative to our policy, where if we just measure entropy, it just tells us the entropy over this at this decision overall. And so what's going on here, again, covering this very briefly and not very formally, but there's two things that we use to get entropy. So the first is the notion of information content. How much information is there in a variable or in a random variable? And then we can ask, entropy is actually the expected information. And what we're going to do is, instead of looking at expected information, we're just going to measure information. So in the case of uniform distribution, then those are actually the same, but when we go to a non-uniform distribution, there'll be something different. So the old approach that we had was, imagine that an oracle's taking us from the top of the tree to the bottom of the tree, and as we go down that path, it's going to tell us what decision to make, and we're going to measure how much it has to tell us. In the new approach, what we're going to do is we're going to think about our tree of policies. So we have a tree that describes what our current policy is, and then we're going to consider a tree where the policy in that tree is actually will always get us to the goal. And there could be many actually such trees. And so in general, we'll think about what is the one that is easiest, that we have to communicate the least to get to. But we're asking basically, how much communication does it take to switch your policy from your original tree to a policy on a tree where you were always going to reach the goal? And so, as I said, we're going to measure the information you have to communicate to get to that tree. So let's look at an example tree. So on the left-hand side, our policy says we're going to go here with 1/4 probability, here with 1/4, and here with 1/2. And there's two goals, goal 0 and goal 1. And the first algorithm we'll look at is the minimum solution information. So we're going to ask, what is the minimum information that I can communicate to get you to a single goal? And in this case, our policy is more heavily weighted on this goal than on this goal. So the goal that we would try to get to would be this one. And the policy we need to get to is this policy right here. So we're going to ask, how much information, given this is my initial policy, do I need to get to this policy right here? And in this case, this is very similar, but a little bit different than what we would do for measuring entropy. And then we think about the broader case. Well, I've got multiple goals here. So when I have multiple goals, since there's no goal down the middle branch, I need there to be 0 probability here. But I need to balance the probability on the left and right-hand side so that I minimize the amount of communication I have to do in order to get you to a goal. And so the minimum expected over the whole tree, or if we were to do this many times. And so that involved running some optimizations, and it ends up in this case that the probability should be 2/3 on the left branch and 1/3 on the right branch. And this will minimize the amount of information I have to communicate to get your policy to be the same as this policy, which guarantees you'll always reach a goal. Now, we can use the Kale divergence to measure the information that's required to basically, there's a couple different ways that you can interpret this, but it's basically measuring the information for shifting the player policy. And I'm going to show the derivation here in practice. These were slides from Junwen's master's defense, and for this talk I didn't have time to go through it, but I wanted to show that we could do this optimization of finding the minimum policy here. And after we do that, then we can compute the new policy and actually compute what the probability should be in that policy. And then we can compute the total solution information. So that's just there to show some of the process that you can find in the paper and you can find in Junwen's MSc thesis. But here's a very simple way of understanding it. So given that I'm playing a puzzle or a problem, or any given problem with a policy pi, I can compute under that policy what's the probability of reaching a goal state. And so that would be P of pi. And it ends up that the information in the solution, that it requires to get to any solution and the minimized information, applying the minimization across the entire tree, so it's the total information, is actually just the negative log of the probability. So it could have been something more complicated than this, and this feels like a result that's probably known in other areas, but this was the result that he came up with through running this optimization. And this is a really nice result because it means now that if I have a policy and when I think about a policy, and maybe I can't actually enumerate the entire tree. Now, for many puzzle games, you actually can't just enumerate the entire tree. But if I can't do that, for instance, I could sample the tree to estimate the probability of reaching a goal state. And so this gives me some notion of the difficulty of a problem having to do with just the negative log of the probability, which means, of course, it's just the probability tells us something about the difficulty, the probability of reaching the goal. But when we put it in terms of information, I think we get units that are a little bit easier to deal with as humans. So let's look at some experimental results that we're then able to do, given that we have these tools. So one of the things we were doing actually to start this work is we were building this tool. And the idea of this tool is that we could take a partial puzzle from the witness, we could put some things down into that puzzle, and then we can put question marks down, and we can say, look, I want to put some other things in here, but I'm not sure what I should put there. And so what the tool is going to do is it's going to exhaustively try putting everything it can put there, and then it's going to sort the results by the total solution information and present them to me in that order. So it's going to give me these puzzles roughly sorted from harder to easier that then I can use to, for instance, choose how I want to complete it. And there might be multiple completions that I could use, and I might have an aesthetic preference or some other preference for which one I want to use, but it'll help me search through that space and find the puzzles that are interesting. Now, as we were doing this, the tool was giving us sometimes puzzles that were a little easier than we expected. And what we realized is that there were more inference rules that were not covered in the tool, and so we added some more inference rules. And I'm not going to go through these in a lot of detail, but for instance here, as you draw a line, it ends up that everything on one side of the line will be in the same region, and you're not allowed to have 3 of these in the same region, but because I have 3 of them on the edge of the line, it means they will be in the same region at the end, even though this region could still be further split. So we can use that as another inference rule. Here we talked about this one before. When you finish a region and move on, then you actually know that that region has to be correct. So in this case, these regions are correct at this point, but this region is not, and so we know that that this would actually not be a legal action to take going up here. What we did then is, in addition to some other things of looking at inference rules, is we took this puzzles here from a site called The Windmill, which has many puzzles which were posted by different players over the years. And this is a test set that was actually used last year by my other student. The number of users over time, active users, has decreased. So there's a normalization that happens to normalize the upvotes over time. We're trying to predict which puzzles are going to be more highly upvoted over time. And I'm not going to present all the results that are in the paper here, but we can start here by looking at one set of puzzles that contain a triangle constraint. So I won't describe exactly what a triangle constraint does here, but when we looked at this type of puzzle, so this is one of our interesting results, is we see that there's a particular inference rule which is very predictive of whether players are going to upvote that puzzle. So it seems that having a good player model on this puzzle, where we know that they're going to use this along the path inference rule, is going to help us predict what the puzzles are that players like. But if we look at the same inference rule on the puzzles that don't have triangle constraints, then we actually don't see a strong difference between the correlation given different inference rules. So, on one set of puzzles, then this is very important. On another set of puzzles, it's not very important at all. There's a number of other results, so validation results and things like that. But one of the other interesting results we had in the paper was to look at the machine learning model that was learned by a 2022 paper by Levy-Lillis. And in that paper, on a very simple set of puzzles, it was learning what's called a bootstrap model. It's basically learning how to search and solve, or an agent was learning how to search and solve witness puzzles, and it was learning a policy. So we took that policy, or we took that model and the policy, and then we evaluated what is the correlation with the information that is required from that policy to go from that policy to solving a puzzle, and how does that correlate compared to when we look at the information required when we get the tree from using our different inference rules. So what we see here is with the best set of inference rules, we get a very high correlation. I mean, these are all pretty high correlations. We got the highest correlation on these particular rules. And but if we used all inference rules, we actually got a slightly lower correlation. But the machine learning policy, now that we have these this information, this TSI, we can put in this policy and we can measure how much information does it take to get from there to the goal. And we see that there's actually a pretty good correlation between puzzles on the windmill website, the number of upvotes they get, and the ML policy, how much information it takes to tell that ML policy how to solve the puzzle. So then we also looked inside this model, and this doesn't use the TSI directly, but we're looking at the model and asking, what is it doing? Like, can we interpret what is going on inside the model? And the answer is we can. So what we're going to look here at is at 4 different scenarios. We're going to see different examples of when an inference rule is going to tell us, for instance, that there's a particular action here, you should never take it. And if you, at that node, if you didn't have the inference rule, then there'd be a 50% chance that you would take, that action or the other action. And we can see here that the policy basically exactly learned this cannot take inference rule. Again, the details are in the paper. If we look at another situation where there's a must take action, we can see the inference rule says you must take it, and the policies basically learn the same thing, even though uniformly there's a 50% probability, or close to 50%. Here's another example of a cannot take using a different inference rule, and we see again here the policy has done a very good job of learning that. But there is this region completion rule. The policy hasn't learned that nearly as well as it has some of these other inference rules. Now, of course, any given inference rule may or may not be predictive of a player in a particular puzzle type, but what we see here, something nice, is that we can now start to understand what this model is learning, that it is learning these inference rules and able to apply those. And I think that's part of why it was able to get such a good correlation between the information and that's required for this ML model to solve the puzzle and the upvotes. So I want to go back to this tool that we built, and I want to talk about something here that it's an insight that we gained. It's not something that we've been able to evaluate more deeply, but let me tell you what happened here. So someone posted on the puzzle. I'd been posting some on the website, some puzzles, and I'd been posting some that I had been playing around and creating with this tool. And they posted this particular puzzle on the left. And so this puzzle has many solutions. It's not a particularly difficult puzzle to solve. And when I saw that, I said, hey, you know what? Maybe we can throw this into our tool. And I'm going to put question marks here to replace these white pieces. And maybe I can come up with something where all the pieces are this orangish color. So we threw this in. It gave us a couple solutions. I found one where they were all orange, and it was highly rated, and put it in and posted it onto the website. And at least at the time of the recording of this video, or the last time that I went and looked at the site, which wasn't too long ago, this puzzle on the left, which has much lower entropy, had twice as many solves as the puzzle on the right did. The number of upvotes, I think we had one more upvote than the puzzle on the left. And this is really interesting, actually, because a factor of 2 of solves is really big. I mean, we're talking about hundreds of solves. And a factor of 2 there is going to be quite a big difference. And as I come back to this puzzle, I actually have a hard time when I come and quickly try to solve this. I have a hard time solving it. And part of the problem that's going on here actually is that there actually are no inference rules that of the ones we've looked at. I mean, there's still some inference rules you can use to help. There's nothing here that really directly guides you or helps you get to where you need to be able to solve this puzzle. And so there seems to be something here about the way humans are solving puzzles, is that we actually don't want a puzzle that is extremely hard to solve. There's no inference rules that will help you, and basically it leaves you wandering randomly. But actually, I think some of the best puzzles are ones where there's a particular inference rule. It may be a hard inference rule, but there's some particular inference rule that you have to learn. And if you know that inference rule, you then can make smart choices to be able to solve the puzzle well. Where this one, when you solve it, like these inference rules were used to basically say we want those not to apply. So this is some of what was going on there. And so there is a notion that we had, it's actually in another paper we had at AIIDE, there's a notion of looking at like the difference in information. So if you know this inference rule and you don't know the inference rule and there's a large difference in information that's required to solve it, then it tells you that that inference rule is really, really important to solving this puzzle. And so now we can think about, for instance, for players, how do we teach them that inference rule? Because that's something that'll be really helpful for them. Or how do we design new puzzles that are not interested in just sort of overall how hard it is to solve a puzzle, but we might be interested in maximizing their need to use a particular inference rule. Like this is going to be really helpful to solve this puzzle, and therefore it'll be interesting as a result. So this is just some insight that we got. We recorded this in the paper just as a point of reflection, and I think there might be more that could be done with this in the future. Okay, so as we conclude here, in this paper, we introduced the notion of the minimum solution entropy and the total solution entropy. And these measures are very effective in the witness for predicting the upvotes that human players are going to give. The nice thing is that it also gives us a mathematical foundation and some generality and allows us now to measure what goes on with inference rules and with policies together. And that's something that wasn't possible previous to this. Some of the questions that we're thinking about after this is how are we going to model players, right? So if player modeling is important, and if we now have also things like differential entropy or differential information that we could use to customize something for a player, we need to be thinking about how we're going to model the players. And another thing, Sudoku and its variants are very, very popular. They aren't necessarily solved in a path in the exact same way that the witness puzzles are, but the player still takes a path of inference through this, and it can still be, the solving process can still be drawn as a tree. So it'd be really interesting to apply this. I think there are inference rules that people use. They're highly named X-wing and Y-wing and things like this that are used in Sudoku. And so I think that's would be a great application domain to look at. And so anyway, this is some of the work that we had at AIIDE this year. Again, congratulations to my student Junwen for winning the Best Paper Award, and look forward to seeing this applied in other domains and in other ways in the future. And if you have questions about this, you're always welcome to contact me or contact Junwen to discuss any of the questions there, or of course you can post on this channel below. Thank you very much.